Howdy. I wanted to go back over what we talked about in class about constant acceleration and do a quick overview of how to read information off of graphs and turn that into 3 equations of motion that we can use to solve problems. And then show you examples of how those equations are used using 2 example problems. When we talk about constant acceleration, we're talking about velocity changing at a constant rate. And that immediately gives us a velocity versus time graph. My velocity at time 0 will start at some initial velocity v0, and then it will grow at a constant rate. And the rate is the slope of the graph, which will be the acceleration, the rate at which the velocity is changing. And because this is a straight line graph, we can immediately write its equation. The velocity as a function of time t is the initial velocity plus acceleration times time. This is a variation of y equals mx plus b with an initial velocity v0 and a slope of a. So the first thing that you want to see about the graph of velocity, which is really kind of magic. We like the velocity graphs because they give us a lot of information. And the first piece of information that it gives us, the slope of the velocity graph, is the acceleration. And the second thing that we talked about in class is that the area underneath the velocity curve, all of this shaded area right here, gives us the displacement. The area under the velocity graph is the displacement delta x. And I mentioned in class that because this shape is a trapezoid, and the area of a trapezoid is the average of its bases times the width, then we can go back to our velocity graph and see that the width here is from 0 to t, and the first base has a height of v0, and the second base right here has a height of v, so that my displacement, delta x, is equal to the average of the 2 bases times the width, which is t. And so this is our second equation of motion. And what I'd like to do now is to show you how these equations would be used to solve a problem. So let's take a look at number 22 in your book here. The car slows down from 23 meters per second to rest in a distance of 85 meters. What was its acceleration, assumed constant? Notice here that because I'm assuming constant acceleration, that is the license for me to use these 2 equations of motion as my mathematical model for the problem. And so I'm going to begin by identifying the information that is given to me. It often helps to draw a little picture of what's going on. So here's my car, and my car is traveling forward at 23 meters per second when the problem starts. We're going to label that information as v0, the initial velocity. And then some distance later, it comes to rest, so that its final velocity is 0. And while it is coming to rest, it travels a displacement of 85 meters. And we know it has to be in the positive direction because the car is moving forward. Now they're asking me for the acceleration. So I'm going to pull out my 2 equations of motion, v equals v0 plus at, and delta x equals v plus v0 over 2 times t. And I'm going to consider how the information that I have here could fit into these 2 equations. And I observe that I have delta x, I have v0, and I have v, which are 3 out of the 4 variables in the second equation right here. So it makes a whole lot of sense that since I have all but 1 variable, I can plug in and find the last variable. Let me write the equation first. So formula then plug in. 5 meters equals 23 meters per second plus 0 over 2 times time. I just pulled that information straight from what I had already observed. And then I solve for the time using calculator, and when I do, I get 7.3 seconds for the amount of time. What does this mean? This time means that it took me 7.3 seconds to get from here to here. We started at time t equals 0, and then time t hit 7.3. We had traveled 85 meters, and we had also slowed to a stop. Well, how does that help me find the acceleration, which is what I was trying to find to begin with? If I now consider the second equation, I observe that together with the time that I computed, I have 3 out of the 4 variables in that equation also. And so I can use the second equation by saying v equals v0 plus at. There's my equation. Plug in 0 for my final velocity, positive 23 meters per second for my initial velocity, unknown acceleration here, and 7.3 seconds for my time. And when I solve for the acceleration by subtracting 23 from both sides and dividing both sides by 7.3, I get that acceleration is negative 3.2 meters per second squared. Why negative? Well, because my car is slowing down, I expect the acceleration and the velocity to have opposite signs. And during this entire trip, the velocity is positive, albeit getting smaller, but the acceleration is negative. So the essence of how we use these two equations of motion to solve problems is simply that we first identify the information. It helps to draw a diagram often. And we identify which equation has all but one of the variables supplied to us. So I look for an equation with only one missing variable. And then I solve what I can solve for. And if that helps me with the second equation, then so be it. So this gives us now a framework for solving problems. The only thing that I didn't like about it is that I had to use two equations, and so maybe that was confusing a little bit. It sure would be nice if I had a third equation that would allow me to solve when I don't know the final. So let's consider coming back and doing a little bit of algebra with the two equations that we have. And in particular, if I take v in this equation and substitute into this equation, watch what happens. I get delta x is equal to v0 plus, now I'm going to substitute v0 plus at for v. And I'm going to do a little bit of algebra here, just clean it up. v0 plus v0 is 2 v0s. And I can write division by 2 as multiplying by 1/2. And now we can distribute the 1/2 and the t to get v0 times t plus 1/2 at squared. This is very interesting for a couple of reasons. One is that it tells us that our displacement will be a quadratic function of time. But also, it allows me to solve for displacement when I am given time and acceleration, but not a final velocity. Let's take a look at problem number 25 here. And number 25 is kind of interesting because it turns out that we can use just one equation of motion to solve. This is going to be a sort of a wrap-up. A car slows down uniformly from a speed of 21 meters per second down to rest in 6 seconds. How far did it travel in that time? So here's my car. And I'm again drawing my diagram. Notice that the reference frame is kind of implied here. Here's my origin, there's my direction, and my scale, of course, is meters. So I have an initial velocity of positive 21.0 meters per second. 6 seconds later, my car is at rest. So what I know is that t equals 0 here, and t is equal to 6 seconds right there. And now they want to know how far did this car travel in that time. So take a look at my two equations of motion. V equals V0 plus AT, and delta x equals V plus V0 over 2 times t. And it occurs to me that I have the initial velocity, final velocity, and the amount of time that it takes to do that. Look at that. This is just a straightforward plugging in. My delta x is equal to 21.0 plus 0 meters per second over 2 times 6 seconds. And that's equal to 63.0 meters. Positive. And we are done. So I hope this was helpful to you.